All right, good everyone. So you're welcome back to this week's class of HPHY404. So today we'll start with the polar representation of complex numbers and the applications in finding the power and the roots of complex numbers. So we can represent, so let's say a complex number can be represented by the plane polar coordinates. So the plane polar coordinates are r and theta. R and theta are the plane polar coordinates. So we can represent a complex number z as r into bracket cos theta plus I sine theta. So if we use the Euler's formula, okay, so with the help of the Euler's formula, which is exponential I theta, the angle, equals cos theta plus I sine theta. So we can write, so let me label this as equation 1, and let me label the Euler's formula as equation 2. So if we use the Euler's formula, which is this, we can write equation 1, which is the polar form of the complex number z, okay, which is r cos theta plus I r sine theta. So we can write it in, so we can write equation 1 in the polar form. So z equals, we wrote it as z equals r into bracket cos theta plus I sine theta. So we can, if we use the Euler's formula, which is cos theta plus I sine theta is exponential I theta. So it means we can write this as r exponential I theta. Okay, so we can write our complex number z as r exponential I theta. So this is a beautiful expression that has huge applications, as you will see shortly. What is the r? The r is the modulus. In the last class, we talked about the modulus of a complex number. Okay, so we said if you represent a complex number z as x plus iy, so where x is the real part, so x is the real part of the complex number, and y is the imaginary part of the complex number z, we said the modulus of z is square root of the square of the real part, which is x squared, plus the square of the imaginary part, which is what? Y squared. So this r is the modulus of the complex number. And last class as well, we looked at the argument, okay, the argument of the complex number. So we said the argz. So in this case, this theta is the argument of the complex number. So r is the modulus of the complex number, and theta is the argument of the complex number. And if you recall, in our last class, we said the argument of the complex number is arc tan, the imaginary part, which is y, divided by the real part, which is what? X. So we looked at this in our last class. So let me label this as equation 3. So this equation 3 is quite useful, okay, in many applications. And I'm going to give some examples of these applications. So the value of theta ranges from, so the values of theta are in the range minus pi in radian, in pi rad, up to pi rad, minus pi rad up to pi rad. Okay, but the rotation by theta is the same as rotation by 2n pi plus theta. What does that mean? It means if you have a complex number written in polar form r exponential I theta, it is equivalent to r exponential I by adding 2n pi. So 2 that is theta, you add 2n pi to theta. Okay, so n can range from 1, 2, 3, 4, and so on. Okay, so this can also be useful. Now, multiplication of and division in polar form. Multiplication and division in polar form. Okay, so if you have two complex numbers, the first complex number is z1 and the second complex number is z2. If you multiply the two, you can write them in polar form. So the first one will be written as r1, so which is the modulus of the first complex number, exponential I theta 1, then multiplied by r2 exponential I theta 2. So you can easily write this as r1 r2 exponential I theta 1 plus theta 2. Okay, so and in the last class we talked about the argument of the product of two complex, the modulus of the product of two complex numbers. We said if you find the modulus of two complex numbers z1 and z2, that it is same as finding the modulus of z1 multiplied by the modulus of z2. And I think we proved this relation by a simple example. The same thing with the division. So if you want to divide complex number z1 by another complex number z2, you can write it in polar form as r1 exponential I theta 1 divided by r2 exponential I theta 2. And we can write this as r1 over r2 exponential I theta 1 minus theta 2. So, and the arguments, the modulus of z1 over z2 can also be written as modulus of z1 divided by modulus of z2. Alright, so I think this is straightforward. So let's take a simple example. So let's say simple example. So let's say we want to find the value of 1 plus I raised to power 8. Raised to power any value. It can be 10, it can be 20. So, for example, if you are given 1 plus I raised to power 20 and you want to start evaluating this by expanding the brackets, it's going to take a long time. But if you write the complex number 1 plus I in polar form, you can easily find the power, as you will see shortly. Solution. So what we do is we'll convert, in this case, z is 1 plus I. Okay, so the real part of z is 1. The imaginary part of z is also 1. So that the r, which is the modulus of z, is square root of 1 squared plus 1 squared. And that will be square root of 2. Now, what about the argument? The argument theta, which is the argument of z, equals arctan of y over x, the imaginary variable 1 over 1. Okay, and what is the value? What is the arctan of 1 over 1? So let's quickly check. So arctan of 1, so that is 45 degrees. So 45 degrees is pi over 4 rad. Okay, so pi over 4 rad. That's 45 degrees. You can convert it to radian. Alright. So we have gotten our r and theta. So the next thing is to write the complex number in the polar form r exponential I theta, which will be r is root 2, then exponential I theta. Theta is pi over 4. So that will be I pi over 4. So if you now want to find this z raised to power 8, then z raised to power 8 will be square root of 2 exponential I pi over 4, everything raised to the power of 8. So if you find this root 2 raised to power 8, okay, that would be 16. So root 2. So let's square root of 2, close the bracket, raised to the power of 8. So that will be 16. Okay, so that will be 16. Then exponential, so this will be 8 multiplied by 8i pi over 4. So that will be 2 I pi over 4, or 2 pi I. Okay, so 4 in 8, that is 2, so 2 pi I. So we have found that 1 plus I raised to the power 8 is just 16 exponential 2 pi I. And 2 pi I, so let me quickly give this here. So if the exponential of 2n, sorry, let me just use in general, the exponential of n pi I can be 1 or minus 1. It is 1 if n is even, and it is minus 1 if n is odd. Okay, so in this case, this n is even, so it means this is 1, so it means this is just 16. So it means 1 plus I raised to the power 8 is just 16. Okay, so you can see, if you are asked to find 1 plus I raised to the power 20, it's the same process. Instead of 8 here, just raise it to the power of 20, and you get your answer. So that is one of the applications of writing the complex number in polar form. Okay, so let me give this simple assignment. So simple assignments. So you're going to submit this assignment. So show that 1 plus root 3i divided by 1 minus root 3i raised to the power of 10 is the same as 1 over 2 plus I root 3 over 2. So please take note of this assignment. So this is your first assignment for today. Okay, all right. So next is the Mover's theorem. So let me change to blue. And roots of complex numbers. Okay, so let's say we have Z1. We have written Z1 in polar form as R1 exponential I theta 1. And we have also written Z2 as R2 exponential I theta 2. So if you multiply Z1 by Z2, then it will be R1, R2. We have written this before. I into bracket theta 1 plus theta 2. So if you use Euler's formula, so we can write this as cos theta 1 plus theta 2, then plus I sine theta 1 plus theta 2. So we can write this. Now, if we generalize this to n number of complex number, so a generalization of this leads to, so Z1 multiplied by Z2 multiplied by Zn. So this will be R1 multiplied by R2 multiplied by Rn, then exponential I into bracket theta 1 plus theta 2 plus theta n, and which can be written as R1 dot R2 dot Rn in bracket cos theta 1 plus theta 2 plus dot plus theta n, then plus I sine theta 1 plus theta 2 plus dot plus theta n. Sorry. Okay, so this is the generalization. Now, if we have z1 to be equal to z2, that's all the complex numbers are the same. Okay, so this becomes, so we have z1 is equal to z2 equal up to zn, which is, we now denote everything by z. So we now have z raised to power n. Okay, so that will be r exponential I theta then raised to power of n, which you can write as r raised to power n then cos n theta plus I sine n theta. Okay, so, and we can, if we use so if we write cos theta plus I sine theta raised to power n, because z is cos theta plus I sine r raised to power r into bracket cos theta plus I sine theta. I think I've written that up here. Yes, so this expression, okay, z is r cos theta plus r sine theta, which in polar form is can also be written as this r exponential I theta. All right, so this cos theta plus I sine theta raised to power n is the same as cos n theta plus I sine n theta. So we call this result De Moivre's theorem. Okay, let me write it here. De Moivre's theorem. Okay, so so what does this tell us? So this tells us that if we want to find the nth root, we can use this De Moivre's theorem to find the nth root of a complex number. Okay, so the general rule is that so let me write the general rule for calculating the nth root of a complex number is W equals, so you find the nth root of R. Okay, so if they say if it is cube root, then it will be cube root of R. If it is fourth root or fifth root, it will be the fifth root of R. Then open bracket cos theta, that is the argument, plus 2 pi k over n, then plus I sine theta. I think I need to use 2 pi k over n. So let me use square bracket for this, and let me use parentheses for this. So in this case, k runs from 0, then 1, 2, then up to n minus 1. Okay, so let me label this as equation, equation 3 or so. Okay, it's an important equation. So you use this equation to find the nth root of a complex number. The nth root of a complex number. So in this case, so W is the nth root of the complex number Z. Complex number Z. Okay. So, and I think R is the modulus of Z and theta is the argument. So K runs from 0. So now K, because if it is square root, if you have to find the square root of a complex number, there will be two results. So K will run from 0 and stop at 1. Okay, we said, so in that case, if it is square root, n will be 2. So K will run from 0 up to 2 minus 1, which is 1. So it should just be 0, 1. So you substitute the value 0 for K, you get your first result. Substitute the value 1 for k, you get your second result. If you ask to calculate the cube root of the complex number, n will be 3. In that case, the k will run from 0 up to 3 minus 1, which is 2. So in that case, you run k equals 0, 1, and 2. Okay, I think that should be clear enough. All right, I think let me illustrate with a simple example. So, simple example as well. So the simple example is that find the cube roots of 8, but technically it means 8 plus I 0. So if you write just the real part, it means the imaginary part is what? Is 0. So let's start from this simple example. Then you can generalize to more complex, complex numbers that have real and imaginary parts. So where the imaginary part is not 0. So how do we find the cube roots? So we need 3 answers. There are 3 answers. The first answer is actually obvious, which is 2, but we have to still work it out. So solution. So we are going to use equation 3. So we need n, we need r, we need theta, we need k. So what is n? N in this case is 3. Okay, because the question says cube root. K will run from 0, 1 up to n minus 1, 3 minus 1, which is 2. So there will be 3 values of k, 0, 1, and 2. What about r and theta? So r is the modulus of z, and z in this case is 8 plus I 0. So the real part, which is x, is 8. The imaginary part, which is y, is 0. So we want to find the modulus of z. In this case, it will be 8 squared plus 0 squared. Okay, which will be square root of 8 squared, which is just 8. Then the argument, which is theta, argument of z, is arctan of 0 over 8. So which is arctan of 0, which is 0. All right. Now, so we have all the values that we need. So all we need to do now is to substitute those values into our equation 3. Now, the first root, okay, so is for k equals 0. So I told you k will run from 0 up to 2. So the first root is for k equals 0, and it is nth root of k, which is cube root of r. So cube root of r is 8. Then open bracket, cos theta plus 2 pi k over n. So theta in this case is 0. So theta plus 2 pi k. K is 0 in this case as well. Divided by n. N is 3. Then plus I sine the same thing. Theta, which is 0, plus 2 pi 0 over n, which is 3. So that the first root will be square root of cube root of real 8 is 2. So I think this question should be written. Let me write the question as let me write it as 8 plus I0. Okay. So so cube root of real 8 is 2. Open bracket, cos 0, which is 1. Then plus I sine 0, which is 0. So it means the first root is 2. Now, for k equals 1, we have w equals still cube root of 8. Then cos theta is 0 plus 2 pi k. K is now 1 divided by 3 plus I sine, same thing, 0 plus 2 pi k. K is 1 divided by 3. Okay, now this will be this will be 2, then cos 2 pi over 3 plus I sine 2 pi over 3. Now, if you are using your calculator for this, you can change your calculator to radian, okay? Because this pi is in radian, so this is pi rad. You can change your calculator to radian, or you convert this 2 pi over 3 to degrees, then you find the cos of that angle in degrees. So I'm going to use my calculator in leave my calculator in radian so that I can easily find the cos of 2 pi. So cos 2 pi divided by 3, so that is minus 0.5, so minus 0.5, then plus I sine 2 pi over 3 sine 2 pi divided by 3, that is 0.866, 0.866. So it means this will be 2 times minus 0.5, that will be minus 1, plus 2 times 0.866, so times 2, so that is 1.732 I, and 1.732 is square root of 3. Okay, so it means you can write the second root. So the first root we got, let me call it 0, and this is 1, 1, 1, 1. So the second root can be written as minus 1 plus root 3I, because root 3 is 1.732. Then you can do the same thing for k equals 2. For k equals 2. So you put 2 instead of 1 here. You put 2. Let me show you. So here, instead of 1, you put 2. Instead of 1, you put 2. So if you do that, you have the W2, which is the third root, to be minus 1 minus root 3I. So that be it. So there are 3 roots. Okay. So the first root is 2. The second root is minus 1 plus root 3I. And the third root is minus 1 minus root 3. So these are the cube roots. So if you have to find the fifth root, okay, of a complex number, there will be 5 results. The square root, 2 results. Cube root, 3. Fourth root, 4 results. Okay, so in this case, we need just 3 results. All right, so let me give an assignment. So assignment. So I think I gave an assignment earlier. So let me call this 1. So this is the first assignment. Then the second assignment is okay. So the second assignment is find the cube roots of let me see the number. So if you say 3 plus 4I, okay, sure, let's find it. So find the cube root of 3 plus 4I. So in this case, the real part is 3, the imaginary part is 4. Unlike the case we treated here, where the real part is 8 and the imaginary part is 0. So here you have the real part is 3, the imaginary part is 4. Okay, so there you are going to obtain 3 results. Okay, 3 values. So that those 3 will be the cube roots. And if you multiply those values, for example, if you multiply 2, okay, if you say 2 raised to the power 3, you're going to get 8. If you say minus 1 plus root 3I raised to the power 3, you're still going to get 8, and so on. Okay, minus 1 plus or minus root 3I. you get 8. Okay, so this is where we stop today. So please submit the assignments in the next class. All right, see you later.